Welcome to another deep dive.
Oh, this looks fun.
Today, we're cracking open a science textbook.
Like a real one.
Yeah, the kind you might find in an elementary school classroom. And we'll be exploring light, shadows, and reflections.
I remember those chapters.
I think you already know everything about these topics.
Well, I know some stuff about light. Who doesn't?
Well, you might be surprised by what we uncover.
Okay, I'm intrigued.
So let's start right where the book does, with a question. How do we actually see objects?
Oh, that's a good one.
We do it all the time, but have you ever stopped to think about, the mechanics of it?
Not really. I guess I just take it for granted.
Right. It's like one of those things you don't think about until someone asks you.
Yeah, exactly.
So the book reminds us that we need light to see anything at all.
Okay, that makes sense.
Like in a pitch black room, even with your eyes wide open.
You wouldn't see a thing.
Right, because it's not enough for our eyes to be open.
You need light, right?
Yeah. There needs to be light bouncing off the objects around us and entering our eyes.
That's how we see. Okay, now I get it.
And that's where the book's distinction between luminous and non-luminous objects comes in.
Oh, yeah. Yeah, I remember that.
So luminous objects,
Yep.
like the sun or a burning candle.
They produce their own light.
Exactly. They actually create their own light, radiating it outwards.
Right.
While non-luminous objects like a tree or your desk,
Don't make their own light.
yeah, they don't. We see them because they reflect light coming from a luminous source.
So it's like the sun's light bounces off the tree, and that's how we see the tree.
Exactly. And it might sound obvious, but think about it. The only reason you can see your hand right now is because there's some light source somewhere. Maybe the sun or a lamp shining on it. And the light bounces off your hand, enters your eyes, and then your brain.
Your brain interprets it.
Yeah, it interprets that information as an image. So this leads to the textbook's activity on different types of objects. It asks you to gather some everyday items, like an eraser, a sheet of paper, or maybe even a drinking glass.
Okay, got it.
And then you try to look through each object at something in the distance.
Like through the glass or the paper.
Yeah. And can you see it clearly? Is it distorted? Can you see through it at all?
Oh, I see. You're testing if they're transparent, opaque, or translucent.
Exactly. So a drinking glass, that's a good example of a transparent object.
Right, because light passes right through it.
Yeah, light passes through it easily, and we can see clearly what's on the other side. But an opaque object, like a wooden block, would block the light completely.
So you wouldn't be able to see anything.
No, you wouldn't be able to see the distant object at all.
Okay, makes sense.
And then there are the translucent objects, kind of the in-betweeners.
Translucent, right.
Yeah. Think of a frosted glass window.
You can kind of see through it, but it's blurry.
Yes. Some light gets through, but the image is blurry or distorted.
I wonder, though, if those categories can change.
What do you mean?
Like, the thickness of an object could influence its transparency.
That's a great point. You're thinking like a true scientist.
Oh, shucks.
For example, a thin sheet of paper might be translucent, allowing some light to pass, but a stack of papers
Becomes opaque.
Exactly. Now, what happens when light encounters an opaque object and can't pass through it at all?
It gets blocked.
Well, yeah, but that's where shadows come in.
Shadows. Oh, this is getting interesting.
The textbook sets the scene. Like, imagine walking outside on a sunny day,
Okay, sunny day. Got it.
and your shadow stretches out behind you, kind of mimicking your movements.
Like a shadow puppet.
Yeah, almost like having a ghostly companion, right?
Mhm.
But how is this shadowy doppelganger created?
Well, I know light travels in straight lines, so...
You're on the right track. When those straight beams of light hit an opaque object,
Like me.
yeah, like you, me, a tree, whatever, they can't pass through.
So that creates a dark area.
Yeah. That creates an area of darkness behind the object where the light is blocked.
And that's the shadow.
And that's what we perceive as a shadow. But there's a detail the book points out that I honestly hadn't really thought about before. You need a screen for the shadow to be visible.
A screen.
Yeah, like a surface. Think of it like this. Imagine shining a flashlight on a friend's face in a dark room. You might not see a clear shadow.
Until you hold something up behind them.
Exactly, until you hold up a piece of cardboard behind them.
Oh, I get it.
That's because the light is being blocked, creating a shadow, but there's nowhere for it to appear until you introduce a screen, like the cardboard.
So the cardboard is like the screen.
Exactly. In everyday life, the ground, a wall, or even the side of a building, they all act as screens for the shadows we see.
Cool. This is making me think about those hand shadow puppets we were talking about earlier.
Oh yeah, the animal shapes on the wall.
Yeah. It shows that shadows aren't always perfect replicas of the object, right?
You got it. The way the light is blocked and projected onto the screen can lead to some fun distortions and unexpected shapes.
That's so cool.
And another activity in the book, it explores how the position of the object relative to the light source influences the shadow's size and shape. They use the example of a long box.
A box, okay.
Yeah, so the shadow is shortest when the long side of the box points directly at the light, which, believe it or not, takes us to our next topic.
Wait, where are we going now?
Because that long box experiment, you can actually modify it to make a super simple camera.
Wait, a camera? Hold on. How do you go from a box in shadows to a camera?
It's actually surprisingly straightforward.
Yep.
So instead of just observing the shadow, you poke a small hole in one end of the box, cover the other end with tracing paper, and voila, a pinhole camera.
So it's literally a box with a tiny hole.
Pretty much.
That's
That's the beauty of it. And when you point the pinhole towards a bright object, like a tree or a well-lit building,
What happens?
you get an image. It's projected onto the tracing paper screen inside the box.
Whoa, seriously?
Yeah. But there's a catch. The image appears upside down
Upside down? Why?
because of how light travels.
Right.
It all comes back to light traveling in those straight lines. The light rays from the top of the object, they pass through the pinhole and end up hitting the bottom of the screen.
Oh, I see. And the rays from the bottom hit the top.
Exactly. Flipping the image.
So it's like a natural optical illusion built into the camera.
You got it. And this reminds me of something else the book mentions. Those patches of sunlight you see under a tree on a sunny day.
Oh, yeah. I love those.
It's like nature's own pinhole cameras.
What? How?
The gaps between the leaves act like tiny pinholes, projecting images of the sun onto the ground.
Wow, I never thought of it like that.
It's a great example of how these scientific principles are all around us, waiting to be noticed.
Yeah, we just got to pay attention.
So we've talked a lot about light traveling in straight lines, but what happens when light encounters a surface and changes direction?
It bounces back.
That's where mirrors come in. Just like pinhole cameras reveal how light travels, mirrors show us how light reflects.
Okay, reflections. I get it.
A reflection is basically just light bouncing off a surface.
Yeah.
This is what allows us to see our reflections in a mirror or on the surface of a still pond.
Makes sense.
And the book has a really neat activity to illustrate this. You shine a flashlight beam onto a mirror in a dark room.
Okay, so the beam hits the mirror.
Yeah. And because light travels in straight lines, you can clearly see the beam hit the mirror and then bounce off in a different direction.
Oh, cool.
So the mirror changes the path of the light.
I bet you could do some cool tricks with that.
You probably could.
Yeah.
The book also mentions an experiment with a comb and a mirror.
A comb. What do you do with a comb?
So you set up a comb on one side of a board and a mirror on the other, and then you shine a light through the teeth of the comb toward the mirror.
Okay.
And what you end up with is a pattern of light and shadow on the board.
Oh, cool. Like a light show.
It demonstrates both how light travels in straight lines and how it's reflected by the mirror.
Wow, that's neat.
Of course, we can't talk about mirrors without mentioning the classic mirror image phenomenon. Have you ever noticed how your reflection seems to reverse left and right?
Yeah, it's like looking in a funhouse mirror, but like a normal mirror.
It's like stepping into an alternate reality where everything is flipped.
So weird.
It's intriguing how a flat surface can create that kind of optical illusion.
Right.
The book touches on this idea, but it saves a deeper explanation for later chapters.
Oh, so there's more to learn.
Definitely. There's so much more to uncover about how light behaves and how it shapes our perception of the world.
I'm ready for more.
Great. Let's take a quick break and then we'll dive into even more fascinating aspects of light.
Sounds good. I need to catch my breath after all this mirror talk. Mirrors are so cool.
Right. They are. This whole conversation about light and reflection has me thinking about how much we rely on these concepts without even realizing it.
Yeah, like they're everywhere.
Exactly. They're just woven into our daily lives. And so many technologies depend on them.
Like what?
Well, like photography, for one. Remember that pinhole camera we made?
Mm-hmm.
It's a super primitive example, but it shows the basics behind how we capture an image.
Oh, yeah, with the light passing through the hole.
Yeah. Light enters through a small opening, creates a focused projection of the outside world onto a surface.
Just like our eyes.
Exactly. And it's the same basic idea behind more complex cameras, too.
So cool.
And then, mirrors are essential in tons of technologies, too.
Besides just looking at ourselves, you mean?
Yeah. I mean, think about it. Everything from everyday household mirrors to, like, high-powered lasers.
Wow, laser.
It's all about the way light bounces off surfaces.
I remember the textbook mentioned a magic device that uses mirrors.
Oh, yeah. What was it called?
A periscope to see around corners.
Oh, right. The periscope. I remember that activity, where you position two mirrors in a specific way to see something hidden around a corner.
It was like having X-ray vision.
Yeah. It's a clever way to show how mirrors can redirect light, like they bend the rules of our usual line of sight.
And that's how submarines use them.
Exactly. Periscopes on submarines, they let them see above the water while they're submerged.
It's amazing how something so simple can be so powerful.
It really is. This deep dive is making me wonder, like, are there other hidden aspects of light that we haven't even thought about?
Oh, I bet there are.
Right. There's probably so much more to learn.
Well, the textbook has a section called Things to Think About.
Oh, I like those sections. What kind of questions does it ask?
Well, one that caught my eye was about transparent objects. We know opaque objects cast shadows when they block light,
Right.
but what happens when light passes through something transparent? Like a glass of water.
That's a good question.
We can still see through the glass, but does the light change in any way?
It makes you think, right?
Yeah. Like, what's going on in there?
There could be all these hidden processes happening that we don't even realize.
Another question I was curious about was about shadows in colored light.
Ooh, colored light.
Yeah. Remember we talked about how changing the color of an opaque object doesn't change the color of its shadow.
Right.
But what if you shine colored light on an object? Would that change the shadow's color?
That's a cool question.
Like, imagine shining a red light on a blue object. What color would the shadow be?
It's like a riddle.
The book also mentioned how shadows can appear different colors at sunset.
Oh, yeah, like a bluish tint sometimes.
Right. And it's all because of something called light scattering.
Light scattering. What's that?
It's where different wavelengths of light are scattered differently by particles in the atmosphere. And it's more pronounced at sunset because the light has to travel through more air.
Wow, that's fascinating.
It's amazing how much goes into something as simple as a shadow.
Seriously. So, if we try to connect all of this back to the bigger picture, what's the key takeaway for you?
I think it's just to stay curious. Don't take things for granted.
I like that.
You know, like, question what you see. Experiment, try things out. Who knows what you might discover?
Well said. I mean, we started with an elementary school science textbook, and look at all the fascinating things we've uncovered.
And I feel like we've only just scratched the surface.
Right. There's so much more to learn about light and how it works.
Speaking of, I'm curious to circle back to the pinhole camera for a sec. The book hinted at a connection between pinhole images and eclipses.
Oh, yeah. It mentioned using a pinhole camera to safely observe a solar eclipse.
But how does that work? Why is it safe to look at an eclipse through a pinhole camera when looking directly at the sun is so dangerous?
That is a great question, and one we'll have to explore in part 3 of our deep dive.
Ooh, cliffhanger.
Stay tuned to see how this simple device can help us safely observe one of nature's most awe-inspiring events. Okay, so back to the pinhole camera and eclipses. I gotta admit, I'm still a little confused.
Yeah, it seems kind of counterintuitive, right?
Totally. I mean, we're always told never ever look directly at the sun.
And for good reason. Looking at the sun, especially during an eclipse, it can really damage your eyes.
I've heard that.
Because the sun's putting out all that intense light and radiation.
Ouch.
And that can actually harm those delicate cells in our retinas.
So how does the pinhole camera make it safe? It's not like it blocks out the sun completely.
Well, it acts kind of like a natural filter.
A filter.
Yeah, that tiny pinhole, it only lets a really small amount of light through.
Oh, so instead of getting the sun's full blast, you're seeing like a
much smaller, dimmer version.
like a mini projection.
Exactly.
Yeah.
And that's what makes it safe to look at.
Wow, that's so cool.
The book even says you can see the different phases of the eclipse with the pinhole camera.
Oh, really?
As the moon slowly covers the sun, yeah.
That would be amazing to see.
It would. And it all comes back to that basic principle we've been talking about.
Light traveling in straight lines.
Right. Focus through a small opening.
It's amazing how something so simple can be so useful.
It is. You know, starting this deep dive, I thought I knew a decent amount about light, shadows, reflections.
Me too.
But going back to the basics, with this elementary school textbook, I've realized there's so much more to learn.
I feel the exact same way. We've learned how we see, explored how light and shadow work together.
And jumped into the world of mirrors and reflections.
And honestly, I feel like we've only just scratched the surface.
There's a whole universe of stuff out there related to light.
Like how light interacts with water and rainbows and...
All kinds of optical wonders just waiting to be explored.
This deep dive has really sparked my curiosity about, well, everything.
I know what you mean. It's not just about the facts we've learned about light.
It's more about that feeling of wanting to know more.
Exactly. It's
Yeah.
about reawakening that spirit of inquiry.
I love that. So, to all our listeners out there, we encourage you to keep those curious minds going.
Don't just take things at face value,
Look closely at the light and shadows around you.
Ask questions, look for answers.
And most importantly, never stop exploring the world around you.
Because you never know what amazing discoveries are waiting to be uncovered.
Absolutely. This has been The Deep Dive. Thanks for joining us.
Until next time.